right, so for each of these, you have to name them as isomers, the same, or unrelated. As we talked about, this one way to do that, a good way to do that, is to name them both and then see if you come up with the same name for both structures. So in this case, we'd find that longest chain, which in this case is 1, 2, 3, 4, 5 carbons. There's no branching stuff coming off. There's no substituents, so that's just pentane. The structure on the right is also 5 carbons in a row, no branching or anything else. That's also pentane. So those two are the same. Right? So even though they might look very different, you have to think about how they're connected to determine if they're the same or not. These two, we not only have to know, kind of put them in the same situation, but figure out their molecular formulas as well. In this one, we've got that structure on the left, and then we've got 1,2-dimethyl 1-cyclopentene. One thing we could do is we could draw the structure on the right. So if it's 1-cyclopentene, that would be like that, and then 1,2-dimethyl means methyl groups coming off like that. So it looks similar to that one. It's certainly not the same because it's connected in a different way. So we know they're not the same. To tell if they're isomers or not, we have to count the number of carbons and hydrogens, or just look and kind of see if they're the same or not. If they have the same numbers of carbon and hydrogen atoms, then they're isomers. If they have different numbers of carbon and hydrogen atoms, then they're unrelated. In this case, they have the same, so they're isomers. So we could go around and count those out, how many carbons and how many hydrogens. Get a molecular formula for each one. And I think if you count this one out, you find that this is C7H12. And this one also comes out to C7H12. Questions on those? All right. And then the last one, kind of like the first one, we're looking at these two structures. They're both continuous chains with no substituents, nothing branching off. So we just have to count the number. They also don't have any double bonds or anything like that. So we can just look at the number of carbons and get the answer from that. So we've got on the left 2, 4, 6, 8 carbons, and on the right 1, 2, 3, 4, 5, 6, 7, 8 carbons as well. So those must be the same. Also. All right, for these, we're going to name them or draw a structure for a given name. 1,1,2,2 tetrachloroethane. How many carbons in ethane? 2. So we're going to draw 2 carbons like that. And then we can number them, 1 and 2. The substituents tell us that at carbon number 1, there's 1, 1. That's 2 different chloros, and then there's carbon number 2, there's 2 chloros. That's the 1, 1, and 2, 2. So we've got 2 chlorines over here and 2 chlorines over here. And that means we also need hydrogens to round out the 4 bonds to carbon. Another way to draw this would be for using a line structure, which would look like this. So 4 chlorines, 2 on carbon 1, 2 on carbon 2. All right, so for then this next one, we have to come up with a name. So we're going to find the longest continuous carbon chain, which in this case is just the one that's straight across here. We also could go down like this. It's the same number. We'll just stick with the most obvious one. And then we're going to number it. Now we have to decide if we're going to number it from left to right or right to left. What do you think? Yeah, we're going to go right to left because the substituents are closer to the right side. So that's 1, 2, 3, 4, 5, 6, 7, 8. That makes this octane if we look up at that chart. And we've got a substituent here and here on carbon 3 and 4. So on 3, that substituent has 2 carbons. That makes it ethyl. And at 4, it has 1, so that makes it methyl. Three ethyl 4 methyl octane would be the full name of that. All right. And then finally, the last one, 3,4-dichloro-1-cyclopentene. So we're going to start with the main part, which is the cyclopentene. And it doesn't matter where you draw that double bond, put it wherever you want in the structure. But we do need to number those 2 carbons so we know, well, we need to number the whole ring so we know which one's which. It doesn't matter where you start your 1 as long as it's on one side of the double bond, and then 2 is the other carbon from the double bond. So we go 1 at the top and then 2 around. And that means we get 3,4-dichloro, so there should be chlorines here and there. What you got? Maybe? Okay. We'll keep practicing this. This will come up again on the quiz next week and then the final. So you'll get more chances to do it. All right. So we talked about a bit of the organic chemistry stuff. We talked about alkenes a little bit with some naming. So there's a few things we didn't get to because I had to cancel class last week Tuesday. And we'll finish that up today, and then we'll be done with this chapter. So that is talking about cis and trans with alkenes, talking about reactions of alkenes, and then aromatic compounds. Those are kind of the last 3 topics of the chapter. So let's take a look at those. First is this issue of working now? Okay, we're working now. Cis and trans. And this answers this kind of a question. So let's imagine 2 molecules here. So there's 2 different molecules. Let's name those 2 molecules. So how would you name the molecule on the left? It's butene. We have to be a little bit more specific than that, though. Where is the double bond in that molecule? Yeah, it starts on carbon number 2. So this one is 2 butene. And what about the one on the right? It's the same, 2 butene. So does that mean that these are the same? In this case, it doesn't, because double bonds don't rotate. So we can't just say, like, twist the middle and make one from the other, because double bonds don't twist like that. So that means these are different molecules. Different molecules that have the same name is not allowed, because you have to be able to say, okay, this is a unique name to just this molecule. So there's this extra thing we sometimes need to use when we talk about double bonds called cis or trans. And so we're going to label these as either cis 2-butene or trans 2-butene using this convention. Cis is going to refer to the same side, and trans is going to refer to the opposite side. And what on the same side or opposite side? Actually, anything where there's 2 of the same. So this could be hydrogens, it could be methyl groups, whatever is connected to the double bond. If there are 2 that are the same, we can call it cis and trans. If they're not 2 that are the same, we have to use some more complicated stuff that we're not going to get into. But what you do is you draw a dotted line through the double bond, parallel to the double bond, like this. All right. And the 2 things coming off of that double bond, in this case, methyl groups, do you see on one of these structures, they're on opposite sides of that line, and on the other structure, they're on the same side of that line? So which one would we call cis 2-butene? The second one, because both of those groups are on the same side of that line. And that makes this one trans 2-butene. And it doesn't really matter what orientation that double bond is in. That's why we draw that dotted line, because sometimes it's not always clear. Let's say we drew a molecule like this. Right. And we want to know if it's cis or trans. We do the same thing. In this case, since we're looking for things that are the same, we want to look at the two hydrogens that aren't shown. But we draw that line parallel to the double bond again. And then we say, okay, those two hydrogens, are they on the same side or the opposite side of that line? Yeah, they're on the opposite side. So that makes this a trans. And in this particular case, this is trans 2 pentene. So that's all that means, is when you have a double bond, you have to look and see if the hydrogens are on the same side of the double bond or the opposite side of the double bond, and then you call it cis or trans. Now, there are plenty of double bonds that don't have this. Take this one, for example, 1 pentene. 1 pentene can't be cis or trans because there's no things on opposite sides or on the same sides. If we look at this one side over here, this has 2 hydrogens on it. They're not shown, but 2 hydrogens there. And then there's a hydrogen over here. So we can still kind of draw that line, but we got the same thing on both sides. So any double bond that has the same thing on both sides on one of the carbons, you can't make that distinction. So this one's just going to be called 1 pentene and doesn't get any special cis or trans treatment.
Does that cis or trans could be only in double bonds?
Right, only for double bonds, and only for double bonds in the middle of chains, where you can have things on opposite sides. So at the end, you're always going to have 2 hydrogens, so there can't be any kind of designation there. So now let's take a look at reactions. We're just going to get to the bare surface on this, but it's really what's exciting and what's important about this whole chemistry, organic chemistry, is that you can take these very specific molecules and you can kind of put them together pretty much any way you want to, almost like little building toys or something. The science has advanced to the point where we really know so many reactions that we can design a molecule however we want to design it. And this is how most pharmaceuticals and drugs and that kind of stuff are designed. Somebody comes up with a structure that we know does some particular thing biologically, and then chemists figure out how to make it from stuff that we can get. So to do that, we use reactions of these functional groups, these parts of the molecule that actually do things, interact with other molecules. And we're going to look at some reactions of the alkenes, of how these double bonds react. We're going to look at 2 reactions specifically, and they're both considered addition reactions.
So if we're like able to design these molecules specific, how come they have side effects?
Well, because just because you can design a molecule does not mean you can control how various things in your body interact with that molecule. So yeah, we might know that this particular, just an example, like a painkiller like ibuprofen, we know that it does this thing with your blood that makes you not hurt as bad, but your stomach also interacts with that ibuprofen and can cause ulcers and that kind of stuff. So the same molecule, we can build that molecule, but we can't necessarily. What?
So we can decide how the body breaks it down.
Yeah, you can't say, all right, stomach, you don't touch this now. Just wait till. I mean, we can in some ways, and that's a part of research, is like figuring out how to do that. But you can't like tell certain cells not to mess with something necessarily. Yes, I don't know. Figure it out. But yeah, so let's look at some of these reactions that we call addition reactions. At a basic example here, we're going to take this double bond molecule, which is ethene, the smallest alkene, just 2 carbons with a double bond. And we can react this with a molecule of hydrogen. Remember, hydrogen is H2, not just H. And this will add together. So in inorganic reactions, we call these composition or combination reactions. In organic, we call them addition reactions, but it's really the same thing. What happens here is that those hydrogens from the hydrogen molecule add to the alkene, so that now it's no longer an alkene, it's an alkane. And this new molecule is ethane. Now, this doesn't just happen spontaneously. You need, well, it does, but it requires a lot of energy. You need a catalyst to really make this reasonable, and the catalysts that are often used are metals. So you'll see something else added to this reaction, like platinum, palladium, or nickel, which are all some different metals. You'll notice all in the same column in the periodic, right in the middle of the periodic table. And those metals help facilitate the reaction. They bind the hydrogen and the double bond, and then it'll kind of allow them to react with each other. So what this looks like in a line structure, since we don't draw the hydrogens, it kind of makes it look like the double bond is just going away. And you can think about that as a way, as kind of a shorthand of thinking about what happens in these reactions. So let's say we have some molecule like that, this methyl cyclohexene. The way you might see it written is that this reacts with hydrogen in the presence of a nickel catalyst in this case. And so the product is those 2 hydrogen atoms added across that double bond, 1 to each carbon. The result of that then is this. It looks like the double bond just kind of goes away, but really more hydrogen has been added. You see how that works? Let's trace those hydrogens around again. When we start, there already is a hydrogen here, and there's no hydrogen on the other side. And now we've added, well, that one has stayed there. We've added another one over here, and then another one over here. Remember, carbon always has to have 4 bonds, so when we draw these line structures, we have to keep in our mind that there's actually enough hydrogens there to fill that 4 bonds to carbon. If those bonds aren't shown, then we have to assume that they're there. Okay. So this process, oops, I should have put it above, but I'll put it over here. This reaction is called hydrogenation. And it's an important component of many organic syntheses, this adding hydrogen to make alkenes into alkanes. This also comes up in things like food. If you've ever seen things like hydrogenated fats, Crisco or shortening, those kinds of things are hydrogenated fats. Those start with unsaturated fats, which are fats with double bonds in them and usually liquids. You hydrogenate them using a similar process to this, and then you form saturated fats from those vegetable fats. So you take a vegetable oil or whatever, you hydrogenate it, and you turn it into shortening, which is now a saturated fat. So you saturate it with hydrogens by adding more hydrogens to it.
This has to be labeled as trans fats, right?
No, not quite. Trans fats are partially hydrogenated fats, which are when you don't do this full process, you kind of do it part way. And what you actually leave some double bonds, but you stretch them out and you turn them from cis double bonds to trans double bonds. And those are known as trans fats. So they have trans double bonds in them, and they're particularly bad for a number of reasons, and we're kind of phasing them out now. And that does have to be labeled on the label trans fats. However, it's rounded with significant figures. So even though a label might say 0 grams trans fat, all that means is less than 0.5 grams per serving. So if you see something in the ingredients that says partially hydrogenated something or other, that means there's some trans fats in there. Trans fats are useful in the food industry because they have nearly infinite shelf lives. They stay shelf stable forever. They never go rancid. That's how we hear about like Twinkies, lasting forever and that kind of stuff. Those kinds of snack cakes, vending machine things that'll just sit in a vending machine like for months and months. It's usually trans fats that are stabilizing those. But the fully hydrogenated fats do not have the same dangers as trans fats. They do have the same dangers as regular saturated fats like butter or animal fats or lard, that kind of stuff. Yeah. All right, so let's look at one other related reaction, which is hydration. What do you think hydration is adding? It's another addition reaction. Yeah, we're adding water. So we'll start with ethene again. And this time we'll add water. And I'm going to draw water in kind of a weird way, and you'll see why when we get to the end of the reaction. But you can think of water as HOH. I mean, we know it's H2O, but we could write it like that. And you'll see why we do that. This reacts with an acid catalyst. So some source of acid is added. Now it's called a catalyst because it speeds up the reaction, and the acid isn't actually used up. So the acid facilitates the reaction, but is not used up. That's the definition of a catalyst, right? Lowers the activation energy, but it's not used up itself. Same with the metals in the previous one. So the result of this is much like the reaction we just did, but instead of adding HH, we add HOH. Instead of an alkene, we have an alkane of sorts. Get my color. And we've added this OH group onto the molecule. Now an OH on an organic molecule is called an alcohol group. The common molecule we think of as alcohol, like drinking alcohol, is ethanol, which is this particular molecule. But any organic molecule with OH groups on it, that's called an alcohol group. That's where that comes
What's
from.
going to be the formula?
What do you mean?
Like C2H.
Oh, yeah, kind of C2H6O. But because it's an organic compound, we'd probably write it CH3CH2OH. We usually like to write it in a condensed form so that it's clear how things are connected. This is ethanol. Or ethyl alcohol, another way of saying that. So let's look at how this looks in a line structure. We'll use our cyclohexane again. So you'll see something like this. You'll see cyclohexane reacting with water, an acid catalyst to form this alcohol. Now, does it matter which carbon we put that OH on, or are those two the same? What do you think? Are they the same or different? They're the same, yeah. So it doesn't matter in this case. the symmetric molecule, you could imagine if you just took one of those and kind of flipped it down, you'd have the other one. So those are the same. Let's look at what happens when we try to do this reaction in something where that's not the case, where it's not totally symmetric. And we'll draw it in a condensed structure here so it's a little clearer at first. Okay. If we look at that double bond, that alkene, one side has a CH3 coming off of it, and the other side doesn't. So there are two different possible products here. Let's look at them and then decide which one is better. So one would be to put the OH here and the H over here, the H on the right. So make that CH2 into a CH3. Or the other possibility is to put the hydrogen in the middle and the OH on the end. And those are now different molecules. Those are isomers. They're not the same. Whether if the OH is in the middle, it's in the middle. If it's in the end, it's in the end. We would call the first one, we would call that 2-propanol, and or isopropanol, and the one on the end we would call 1-propanol or N-propanol. So they're different molecules. In this particular reaction, only this one is really formed. This one is the major product. And there's a variety of reasons for that. We're not going to get into that in this class. If you go out and take organic chemistry, we'll talk all about that. But what we can do is we can think about how to decide which one goes where. And there's like 2 different ways that people remember this. So you can decide whichever one sounds less confusing to you. Some people like to think of it as the OH goes on the carbon that's connected to the most other carbons. Do you see how that works here? The OH goes in the middle carbon because that carbon is connected to other ones. The other way you can think about it is the hydrogen goes to the carbon with the most hydrogens connected to it. So the hydrogen from the H2O went right here because over here that carbon had 2 hydrogens and this one had just 1. So whichever way you like to keep that straight, and you can take a look at it in the book and do some practice with that. Let's look at how this would look in a larger structure with a line structure. So let's take a cyclohexene type structure, but we'll add a methyl group to it right there, make it methyl cyclohexene. And now those 2 sides of that double bond are different. So the bottom is different from the top in that double bond. So we have to make this decision if we're going to do a hydration reaction of which carbon the OH goes to and which carbon the H goes to. So what do you think? Does the OH go to the top carbon on that double bond or the bottom carbon on the double bond? It goes to the top, right? Following that same rule as before. All right. Now, since we often think about these reactions in terms of synthesis, that is, making something that we want to make, a lot of times we don't necessarily want to know what's the outcome of a reaction, but rather we want to think about what could we start with to make this thing that we want. So let me give you a possible product here. Let's say this is the molecule that we want to make. This is our product, our desired product of our reaction. We know we want to make it from some kind of alkene. So we want to add an alkene to water with some acid catalyst and make this molecule. What molecule should we start with? What do we start with to make this? See if you can draw a molecule that would make this. And if you get one, there's actually tools that would make the same product when they undergo hydration. Anybody want to come draw one? No, no one else can draw it? You're not confident? All right, if I give you one, do you think you can find the other one? All right, so there's two possibilities here that we could use. One of them, kind of like the problem above, you could take that alkene. Because if you imagine what would happen if you add water to that, you'd get an OH on one side and an H on the other side. The OH would go to the one with the most other stuff attached to it. So that's right here. And that gets you this product right there. So that's one way to do it. What would be another way to do it? What's another possible product? But yeah, I think. Right, so you could have the double bond coming off on the chain like that. Same idea. If water were to add to this double bond, you'd have an H over here and the OH here, which would be the same product. Those are the only two reactions that we're going to look at of alkenes. So make sure you get some practice with those from the book, and we'll have a quiz next week that'll have some of this stuff on there. All right, last part of this chapter then is called something called aromatic compounds. What do you think that refers to? Any ideas based on that language? What's an aromatic compound? Oxygen? Okay, why?
Air.
Oh yeah, from air. Okay, sure. Makes sense. That's not quite right, but yeah, it makes sense. What else can aromatic mean? That's a good thought. Yeah, it means smells, like something that has an aroma that smells. That's actually neither of those. That's not a good definition for this either, even though that is where this word comes from. But it's kind of a common source of confusion because there's lots of stuff that smells that would not necessarily be in this category. So this category, when we talk about molecules, refers exclusively and specifically to rings with alternating double bonds. So a ring structure like a cyclo whatever that inside has alternating double bonds. The kind of most common classic structure is this one, which is a cyclohexane with alternating double bonds. That means it has one hydrogen on each carbon. And in a condensed structure, it would look like this. And those double bonds can be written either of two ways. It can be written like that, or we could kind of flip them, move everything over one carbon. And the fact that it can do that means that this has some special properties. Those electrons in those double bonds have a way of moving around the ring or occupying all the space of the ring that makes this especially stable. That's what's special about these compounds, is they're especially stable. They are harder to react. If you expose benzene to water and acid, the double bonds in benzene don't react the way that regular double bonds do, because it's too stable. It can't do anything. So because of that, it has some special properties, and it can exist in all of these different things. So this is a common piece of a lot of parts of our body. Some amino acids have this in it. A lot of pharmaceutical type things, other small molecules that interact with our body have this in it. A lot of things in nature have this kind of a structure. Because it's so stable, it becomes very common. There are a few other molecules that have this structure that kind of get their own names when they get these structures. So if we put a methyl group on benzene, we don't call it methylbenzene. We call it own name, toluene. Although really we could call it methylbenzene. Toluene is an important component of, these are good solvents, they dissolve things. You'll find this in glues. If you ever like build plastic models, that kind of stuff, and it has that model glue with that very specific smell, that's toluene. If you hear people like sniffing glue, that might be what they're doing, that might be part of it. It's not a good idea. These things are generally carcinogenic. Toluene, not so much, but benzene certainly is a carcinogen, so we don't use that as much anymore. It used to be a very popular, very commonly used solvent. People like in my parents' generation, my dad would talk about that they would just have a bucket of benzene at the door of lab, and after they did their lab, everybody would just kind of like wash all the stuff off in the giant vat of benzene. So we don't do that anymore, which is good. So toluene, you can actually get toluene, I think, like at a hardware store. It's a relatively common solvent. If you put an OH group on benzene, you have what's called phenol, which you may have seen in parts of molecules in cosmetics and things like that. Makes an interesting bridge between what's called a hydrophobic part, or a non-polar part, the benzene, and a hydrophilic or polar part, the OH. And so that can have some interesting properties as well. As these molecules get bigger, they can start to pose some other problems. So like, if you hook two of these things together like this, you have a molecule called naphthalene, which used to be made into something called mothballs. I don't know if anybody's ever seen any of those lately, but they used to have these things called mothballs, and you would put them in your closet or drawer or whatever, and the naphthalene vapor would keep the moths from like eating all your wool and canvas stuff. This is also not great for you, so we don't really use mothballs much anymore. But as these get bigger, because they're stable, they're formed from combustion. So you can make these kind of pretty looking honeycomb-like structures. These are called polyphenylenes. And these kinds of things, remember we talked before about combustion reactions, where you take a hydrocarbon, like a fuel or wood or whatever, and you burn it, and then you form carbon dioxide and water. But then we also talked about how like in the real world, when you burn something, it doesn't just turn into carbon dioxide and water because it burns incompletely. So it turns into ash, like blackish kind of ash stuff. Even like in lab, when we use the Bunsen burners, if we don't have enough oxygen mixed in, the flame is too yellow, you get like black soot on it, everything. Well, that black soot contains a lot of these kinds of molecules, those and bigger ones, and those are carcinogens. This is one of the major sources of carcinogens in things like cigarette smoke also, because when you inhale a partially burned thing, you're inhaling a lot of these kinds of molecules. That's also why things like charred meat are also not good for you, or like cooking meat over a barbecue or like a charcoal grill is also a source of carcinogen. And remember, we talked about this. Doesn't mean it's going to kill you necessarily, but it does mean that there is a risk associated with having these molecules, eating these molecules from those sources or inhaling those molecules. Another one that comes up sometimes environmentally, if you hook benzenes together like this, that's known as biphenyl. So you've got naphthalene when they're like stuck together sharing 2 carbons. You've got biphenyl when they're not sharing any carbons. And we can put chlorines on here. And these were important industrial products and starting materials and solvents. And these are known as polychlorinated biphenyl, or PCBs. You might have heard of those as environmental toxins. There are a lot. They were put into water supplies a lot, especially around in the Midwest, by companies doing various processes many years ago. They don't really break down in the environment. They are dangerous to people if you get too much of them. And so if you fish a lot or do any fishing, sometimes in bodies of water and rivers, you can get guides about what kind of fish are safe to eat. And like some say, only eat 1 of these every month, or only eat 1 of these per year, or I don't know if you've ever seen stuff like that about fish, but it has to do primarily with how much of these types of molecules are accumulating in that fish, as well as things like mercury and lead. But these are some of those things that end up polluting the water systems. All right, so we'll stop there. That's a basic introduction to the organic chemistry stuff. So next week, just to review the schedule again, on Tuesday, we'll go over the exam from last Tuesday. We will check out of lab and we'll do the nuclear chemistry experiment together. So bring the instructions in your write-up and stuff for the nuclear chemistry lab. You won't have anything to do at home from that. We'll get it all done just during that time, and then you can turn it in before you leave. But bring in that paper for that so we can finish that up. Then on Thursday, that'll be the last day of class. We will have a quiz on this second half of this organic stuff mainly, and we will that will be the time to review, ask questions about getting ready for the final. Our final will be the following Tuesday. It's not exactly at this time. It's so let me show you that. You go to, where is it? Academic calendar. There's a final exam schedule, and this is so exams in different classes don't overlap. But because we're all in here during this period for lab, this is our final exam period. So it will be Tuesday, December 15th from 1:45 to 3:30. And I don't have final confirmation on this, but it should be up in the lab room. It'll be in one room on the 3rd floor up there. Hopefully it'll just be in the same lab room. If not, I'll let you know.
It's going to be the same, like 25 answers, like.
It'll actually be a little bit shorter because you'll notice this time period is shorter than what we normally have for our labs. So it'll be a shorter exam. It'll be primarily multiple choice to try to fit it in that framework a little bit better. Because this is what, 2 hours, this is an hour and 45 minutes, and usually we have 2 hours and 45 minutes, so it'll be a little bit shorter. Yeah, so that's our exam, and that will be it. So then final grades are due the next Monday. So happy studying, and I'll see you on Tuesday. We're not going to get into the next chapter, so this is the end of the new stuff for this class. So just focus on going back and studying and catching up to get ready for the exam.
Would a polymer have